So today we're going to be looking at related rate problems and finding basically an unknown rate of change. We will be given some rates of change in terms of the other variables that will be given, but it's ultimately looking at rate of change problems. The most classic example is when you have a ladder leaning against a wall and looking at how fast the top of the ladder changes in its vertical displacement when it's being pulled away at a constant velocity. At time 0, 1, and 2, the distance between those will be the same. Same when we get to time 3. The distance is going to be the same horizontally, but what's going to change is the vertical aspects. So, say for the first one, we may end up looking something like that. The distance here vertically are not the same. It's getting a little bit larger as we go through, and eventually you're going to plateau and you're going to get flat to the length of the ladder. So, we're going to look at these types of problems. So let's now say our ladder is 10 meters long, and the bottom of the ladder is 1.5 meters from the wall at the initial time. So what we have then is a wall with a ladder beside it with a distance of 1.5 meters away from the wall and 10 meters here. It is a right angle, so there is a nice relationship between our height and our base and our ladder length. We also know that it's being pulled away at a constant rate of 0.6 meters per second. So our derivative of x with respect to time, our horizontal component, is going to be equal to 0.6 meters per second. So for every second, we're traveling 0.6 meters away from the wall, horizontally. So, since we know the dx of dt, what we need to find ultimately is our dh dt at t equals to 2. So the relationship between the x and the h is based on Pythagoras. We know that x squared plus h squared is going to equal 10 squared, no matter what. If we differentiate this and we take the derivative with respect to time, for both of these, left-hand side and the right-hand side. So then, if I implicitly derive this, the derivative of x squared with respect to t becomes 2x dx dt, and if I implicitly derive this with respect to t, I'll get 2h dh dt, which is then equal to 0. From here, I can then look at what I know. I know this portion here, dx dt. So 2x 0.6 plus 2h dh dt is equal to 0. So then as a result, if I isolate for dh dt, so by isolating for dh dt, I'll move this to the other side, so I get negative 1.2x, and I divide by 2h. The 2 and the 2 technically can cancel out, so then you're left with dh dt is equal to negative 0.6x all over h. So since we want to figure out now at time equals to 2, we need to consider a few things here. We've got our dh dt is equal to 0.6x all over h, which means we need to know what x is and what h is when time is equal to 2. Now the x means at time equals 2 seconds. So in order to find your x coordinate, we know that we're starting at 1.5 meters away from the wall, and that we're moving at 0.6 meters per second away from the wall. So 0.6 times by 2 seconds, we'd have 1.5 meters plus 1.2 meters. So our x value at this time will be 2.7 meters, will equal my x. My height, we can then use Pythagoras to figure this out. We'd have 1.5, sorry, 2.7 squared for my x plus my h squared is going to equal 10 squared, and you can isolate for your h. That will then go in there. So as a result, our height is approximately 9.6. So our dh dt at time equals to 2 is going to be negative 0.6x, which is 2.7, all over approximately 9.6, so we'll make this an approximation, which then gives us negative 0.16875 approximately meters per second. And it's an approximation because I have rounded halfway through. Another example that people look at as a common example is when you look at having a cone and that you're filling up water into the cone. The higher you get up, the more there is to fill. There's a larger circle that you have to actually fill up before you can get to the very top, whereas at the bottom these little circles are smaller. So the rate of time, so the height based on time, is going to slow down or appear to slow down as you're filling it up. So a couple of things that you need to be able to label in your diagram. You need to have your radius, you need to have your height. So some information that we know: the overall height of the actual cone in this particular example is going to be 15 meters. And we'll be looking at a cross-section as we're growing, getting larger. And we have a radius initially, or at the top I should say, of 6 meters. And we have our unknown radius and our unknown height of the smaller one as we are filling up the cone. We also have a rate of 5 meters cubed per minute, which is going to be, so we have a rate of 5 meters cubed per minute, which is your derivative of your volume with respect to time. So they've given us this rate of change. So now we know our time is in terms of minutes and our volume is in meters cubed. So what we're trying to find is the rate of change of the height with respect to time. And specifically, we're interested in it at a particular time, or sorry, particular height of 7 meters, how our rate of change is occurring. So we do need to know a little bit about the volume of a cone. Volume of a cone is going to be 1/3 area of base times your height. Area of base is pi r squared times your height. So we're going to have to take the derivative of this with respect to time. Now the problem that occurs here, if I take the derivative of this with respect to time, of both sides of the equation, is that we actually have an extra variable. We want the derivative of the height with respect to time. We have the derivative of the volume with respect to time. This little r here is going to put a little wrench in the equation. So we need to somehow figure out how to eliminate this. Well, if we look at our diagram, we actually have similar triangles. Smaller triangle, larger triangle, they have the same ratios. So the 6 to 15 is related to the radius to our height of the smaller triangle. Now these ratios, you can set it up as 6 to 15 is equal to r to h. So if we isolate for r then equals 6 over 15 times by height. So we can actually plug that in and use that as part of this equation. So now that we're down to the two things that we want to work with. So now we have our derivative of the volume with respect to time. We still need to take the derivative of this side with respect to time, but I'm just going to plug in a little bit pi over 3. My radius is now 6 over 15 height squared times by height. We can actually move our constants out front. So pi over 3 can come out front, times by 36 over 15 squared. And then we're taking the derivative of h cubed as a result. So this becomes a little bit easier to work with now. Now I can take the derivative of h cubed with respect to time. So I can then say my derivative of my volume with respect to time is going to equal, and then this also cross reduces, so you're left with 12, that becomes 225 which also reduces down a bit more. So 12 pi 225, I'll reduce that in a second, multiplied by 3h squared dh dt. So now if I multiply the numerator by 3, you get 36 over 225 pi h squared, which then reduces down to, what is it, 4 over 25? H squared dh dt. Now again, we are given the information about dv dt, which is 5. And we have 4 over 25 h squared dh dt. We want to get dh dt by itself, so we end up with dh dt equals 5 divided by 4 over 25 h squared. And again, we want to be able to solve this when your height is 7 meters. So dh dt, it's all in terms of one variable, is 125 all over 4 times 7 squared, which would then give you approximately, let's see, 125 divided by 4 times 49, dh dt 0.638 at that moment in time. It's height to time, so it's meters per minute in this case.